In a previous video we looked at the stationary points of this particular function here. We referred to this graph and we actually calculated some of the stationary points. This point A is a local maximum. Points D and C are called saddle points. Point B is a local minimum. Now we got both partial derivatives of this, set both partial derivatives equal to 0, solved, and we got the coordinates of 4 points. And by referring to this computer generated graph, we could match up the coordinates with each point, and we could tell which is a local max, which is a saddle point, and so on. In this video we will use this formula to classify the stationary points. So this formula involves second partial derivatives. So basically we calculate this quantity here at each stationary point. This quantity is referred to as D. If D is less than 0, the stationary point is a saddle point. If both D and the second partial derivative of f with respect to x are greater than 0, the stationary point is a local minimum. If both D and the second partial derivative of f with respect to x is less than 0, then the stationary point is a local maximum. If D equals 0, the test is inconclusive. So let's take this example here. F of xy equals x to the 4 plus y to the 4 minus 36xy. We are given the coordinates of its stationary points. Well, we're given the xy coordinates of its stationary points. We need to calculate this quantity D, so we need to take second partial derivatives. So we need to start off by getting the first partial derivatives, df dx or f sub x and df dy or f sub y. Well, if we differentiate this with respect to x, we get 4x cubed for this term. This term goes to 0. Differentiating this with respect to x gives minus 36y. Then we can take df dy or f sub y. So this goes to 0. Y to the 4 becomes 4y cubed. Differentiating this with respect to y, x is just a constant, so we get minus 36x. Okay, so they're the first derivatives. Now let's take the second derivative. We need to differentiate this with respect to x, so we get 12x squared. Let's get fyy, so we differentiate this with respect to y, get 12y squared. Now we need to take the mixed partial derivatives, so this here is fyx. So we could differentiate this here with respect to y, or we could differentiate this here with respect to x, because f sub xy is the same as f sub yx by Clairaut's theorem that we proved in an earlier video. So let's say differentiate this with respect to y. Well, that's easy. We just get minus 36, and you can see that the derivative of this function with respect to x is also minus 36. Okay, so here's d, and we calculate d. Well, we have to calculate d for each of the stationary points. So let's see what d is. It's f sub xx multiplied by f sub yy. So it's 12x squared by 12y squared. That's 144 x squared y squared. And then we have minus the mixed partial derivative squared. 36 squared is 1296. Well, we could of course just work out d like this. Note down f sub xx. We actually need f sub xx as part of the test, so that comes into the test here when d is greater than 0. So anyway, if we plug 0 in, we're going to get d equals minus 129, as you can see, which is negative. If we plug minus 3 in, well, we just plug minus 3 in for x and minus 3 in for y, and I don't know what that is, but if you calculate that, you can see that this term will certainly dominate. This term will be positive. It will dominate over this term, so obviously d is going to be positive. We don't even have to calculate that. What about the point 3, 3? Well, that's also going to be positive. 3 squared times 3 squared times plus 144. That's going to have much greater magnitude than minus 129. So d is going to come out positive there as well. So when d is less than 0, the stationary point is a saddle point. So obviously the stationary point 0, 0 is a saddle point. D is less than 0 there. Now if d is greater than 0, we have to look to f sub xx, the second derivative. Look to the sign of it. We can see that f sub xx is positive when d is greater than 0. And if we go back up here, if d is greater than 0 and f sub xx is greater than 0, the stationary point is a local minimum. So it looks like we've two local minima, because for two stationary points d is greater than naught and f sub xx is greater than naught. So these 2 points are local minima. Let's take this example here. We are given the stationary points. They are 1, 3 and 1 minus 3. To classify them, we need these second derivatives. So let's get f sub x. We differentiate this with respect to x. Well, we're going to get 3x squared minus 3. To get f sub xx, we differentiate 3x squared minus 3 with respect to x. Well, that's going to give us 6x. Now, let's look at f sub y. Differentiate this with respect to y will give you 2y minus 6. Differentiate that with respect to y again, 2y minus 6 becomes 2. Now, what about f sub xy? Well, we could take this here and differentiate it with respect to... Actually, sorry, we need to differentiate f sub y with respect to x. Well, we saw that f sub y is 2y minus 6. If you differentiate 2y minus 6 with respect to x, we get 0. And you can check that you'll get 0 if you do that the other way around. If you were to take f sub x, which is 3x squared minus 3, differentiate that with respect to y now, you will also get 0. F sub xy is equal to f sub yx. Next, we can make out this table, which will enable us to calculate d. So here is the quantity d that we need to calculate. So we can tabulate these second derivatives. So we work out these second derivatives for the two stationary points that were given. So for 1, 3, f sub xx is just 6 times 1, which is 6. F sub yy is just 2. It's always 2. F sub yy is constant, no matter what point we're dealing with. And as for f sub xy, that's also constant, that's always 0. Now for the point minus 1, 3, well, we just need the x value to get f sub xx. 6 by minus 1 is minus 6. F sub yy is the constant 2. F sub xy is the constant 0. Now we need to calculate d for both of these points. So we need to multiply 6 by 2 and subtract 0 squared. Well, that's going to be positive. So d is going to be positive for point 1, 3. As for this point here, we multiply f sub xx by f sub yy. That's going to give us minus 12. Subtract 0 squared. Well, that's going to come out to be negative. So remember, if d is negative, it means we have a saddle point. So minus 1, 3 is a saddle point. If d is positive, we have to look to f sub xx and see if it's positive or negative. So here's the condition. If both d and the second derivative is positive, then the stationary point is a local minimum. That's the case here for the point 1, 3. So the point 1, 3 is a local minimum. Here is an example of a function for which the second derivative test fails. By taking the first derivatives df dx and df dy, setting both of them equal to 0 and solving, you will find that there is only one stationary point, the point 0, 0. If you calculate the second derivatives at the point 0, 0, you will get 0 for all of them. That means that d is equal to 0. See, if this is 0, if these three are 0, then obviously d is 0. And we know that if d is 0, the test is inconclusive. So we cannot tell what kind of a stationary point 0, 0 is from that test. However, we can observe that our function is actually a square. We can write it as x squared plus y squared all squared. So that means this function is always greater than or equal to 0, no matter what values xy we used, because we're squaring. So the smallest value that this function can have is 0, and that occurs when both x is 0 and y is 0. So that tells us that the point 0, 0 is actually a local minimum, and it's actually a global minimum as well, because all other values xy give greater values for f, give values of f that are greater than 0. Only at 0, 0 is the function equal to 0. Otherwise the function is greater than 0.